Okay. Can you see my screen?
Yes.
Yes. Yes, sir. Can you see my screen?
Yes, I can see it.
Okay. طيب. بسم الله الرحمن الرحيم. In today's lecture, we're going to, inshallah, continue talking about RL and RC circuits, the step and the natural and the step response of these circuits. But before we start, did you guys have a chance to review what we did last time? Yes or no? Okay. So it's very important. I'm assuming that no, since nobody answered, I'm assuming that the answer is no. So before we start, Shabab, it's very important that you keep, you study on a daily basis. So we're moving in a fast pace because this is a summer semester. Yes, the midterm is something that you need to prepare for. But at the same time, if you spend 20 to 30 minutes, like just reviewing what we did in the lecture, that could be very useful. So you don't need to actually worry about getting back and like starting studying things as if they were like the first time, as if it was the first time you encountered such new topics. Data.
Yes, Doctor. Are we going to have a quiz in the week after the midterm next week?
If it's in the syllabus, then yes, inshallah.
Okay.
Okay. طيب. Abdulaziz?
Yes, Doctor. Regarding the quizzes, is there a possibility to add more quiz?
No, we cannot. You can see that the duration for each quiz is taken almost like half of the lecture time. We cannot sacrifice 3 or 4 lectures. It's really impossible to do that.
No problem if it's outside the class time.
Believe me, it's a problem. Okay. Let's postpone these discussions until later. So let's not rush into the conversation. Okay. In the previous lecture, what we did was we talked about what happens. So let me just go over what we did in this course. So we started with DC analysis, power, energy, voltage, current. Then we studied like resistors as a circuit element that resists the flow of charges. Then we kind of like studied a different combination of resistors and different combination of resistors, meaning that resistors in parallel, resistors in series, and some associated laws or rules that's going to be very, very useful in our analysis. Then, starting from chapter 4, we said, well, so far the circuits that we had were kind of like simple, so we did not need to spend so much time on analyzing them. So we started with some complicated circuit, and we looked into some mathematical simplifications or mathematical techniques that simplify the circuit analysis. And this is what we did with mesh and node voltage methods, mesh current and node voltage methods. Then we moved to some, in these two methods, we were trying to simplify the way we calculate circuits. Then we moved to source transformation, and we said, like, in that specific method, we're trying to simplify the circuit itself. Then we concluded the chapter with 2 important topics. The first one was superposition, which is something that should make sense to all of us. If you have 2 sources, then the contribution, 2 independent sources or 2 linear sources, then the contribution of these two sources is equal to the individual contribution, is the summation of the individual contribution of each one of them. And the most important thing was finding the Thevenin and Norton equivalent circuit. We said, well, oftentimes we are not concerned about the internal structure of the circuit. So we are concerned about what happens between two terminals. So what we try to do, we try to model a very complicated circuit with a resistor in series with a voltage source, and this is what we call Thevenin voltage, or a resistor in parallel with a current source, and this is what we call a Norton equivalent circuit. And then we use the notion of Thevenin and Norton equivalent circuits to derive the maximum power transfer condition. Then, starting from chapter 6, we introduced capacitors and inductors. We said, like, those are energy storage elements. So those are additional two elements. So remember what we had? We have three passive elements: resistors, capacitors, and inductor. And resistor is an element that dissipates energy, that dissipates power. A capacitor and inductor are elements that store power or store energy. So for the capacitor, it stores the electric energy. For the inductor, it stores the magnetic energy. And in the previous lecture, so we studied them, and we studied the current and the voltage relation, then power and energy as well, and the combination of capacitors and inductors in parallel or series. Then we started talking about, well, so far the circuits that we've studied was, we are at the something called steady state. The switch or the source been connected to the circuit for a very long time, everything is stable, everything at equilibrium at this state. So let's study what happens if you have a source and you disconnect the source. So what happens in this short period from disconnecting the source to, say, like 5 or 10 times something called the time constant? And that's what we cared about last time. And we studied the case where we have a resistor and an inductor in the circuit. And from the analysis, we said, like, this kind of behavior or this kind of response is something called the natural response of the circuit. So you have an inductor, you have a resistor, and say, for example, here, let's draw it in a better way. Something like this. So there's a switch, and the switch at t equals to 0 connect the inductor to this circuit and disconnect the inductor from this circuit. So the inductor was initially charged, then discharged. And this is the case we studied last time. And we said, like, we are the key quantity here is the current passing through the inductor. And the current passing through the inductor has the following form. So it has a constant coefficient here, I naught, and this I naught is the initial current passing through the inductor. And remember, the current passing through an inductor cannot change instantaneously, meaning that at t equals to, or at t equals to 0 negative, which means immediately just before opening or closing the switch, and the current should be equal to the current immediately after closing or opening the switch, and this is called, and we call this one I naught, the initial current. The other quantity that we need to find is something called the time constant, and the time constant is, in this case, tau, is L divided by R. Again, L here should be L equivalent, R should be R equivalent. So meaning that if you have inductors in parallel or inductor in series, then you should take their equivalent inductance And if you have a resistor or resistive network, then you need to take the Thevenin equivalent resistors. From that, we can derive the voltage, and we saw that the voltage was 0 for just before the switch is open, and it's equal to, if you take the current and differentiate it, you should get this expression, and evaluate it at 0, you should get this expression. And we said, well, the condition or the restriction we had was the current cannot change instantaneously, but the voltage can actually change instantaneously. So this implies that at the moment when the switch is open or closed, the voltage is not divided. Okay, this is what happened with the inductor, with RL circuit, a circuit that has inductor and resistor. So let's see what happens if a circuit has a capacitor and a resistor. So of particular interest to us is this circuit. So let me bring it here. So this is a circuit that we are interested in. So we have a voltage source, and we have a switch and capacitor and 2 resistors. So at t less than 0, the voltage source is connected to the capacitor to R1. Then at t equals to 0, the switch has moved to position B, and the source is disconnected from, and the capacitor and the sources are disconnected. So the capacitor was accumulating charges. The capacitor was charging until t equals to 0, and at t equals to 0, the capacitor, when it moved to position B, it started discharging. So to determine the response of the RC circuits here, you need to follow the same steps that we did last time. So I'm not gonna repeat them. They are actually in the textbook, but I just want to write this comment here. So you need to apply node voltage method. So you take this. So this is the case for t less than for t greater than 0. This is what happened for t greater than 0. And if you apply the node voltage method here, you have 2 nodes actually, or you can apply this one and that one. So you will see that if you set this one as a reference, you know the voltage, or you assume that you know the voltage. So if you apply the node voltage method here, you will see that this is the, you have only one equation, and if you apply KCL, you will see that the current through the inductor is C dV by dt, plus the current through the resistor is I, which is in this case V divided by R equals to 0. And this gives you the differential equation that you need to use to solve for. You need to use to apply the mesh, or you need to use to find the voltage, to find the expression for the voltage. Remember here, the key quantity that we need to find is actually the voltage across the capacitor. Remember, in the case of the RL circuit, the key quantity was the current through the inductor. So it turns out the solution and everything is exactly the same, but you need to change 2 things. First of all, you need, or actually 3 things. First of all, you need to change this one from being a current to a voltage. You need to change this one from being the initial current to the initial voltage, and you need to change the time constant. So the time constant here is R multiplied by C. It used to be L divided by C. So here is the distinction between the two cases. If you have RL circuit, then the time constant is L divided by R. If you have an RC circuit, then the time constant is R multiplied by C. So you may ask yourself, what's the initial voltage here? The initial voltage is clearly at t less than 0. If you draw the circuit here, you will see that you have R1 and you have the capacitor here. So since since the switch has been at position A for a very long time, so the capacitor, we have a DC source, so the capacitor will look like an open circuit here. And the voltage here will be equals to the source voltage. So this is the initial value of the voltage. So now, if you know the voltage across the capacitor, can you find the current?
Yes.
Yes, I equals to C dV by dt. So this is important, the time constant. And if we write it with the time constant, then we have this equation. So the current, in this case, you have two options. The first one is you can differentiate the voltage, and in this case, you'll get the current. Or you know that the current is by Ohm's law, because the current here, I, is going to be the same as the current passing through the resistor. So you can use Ohm's law to find the current. So in any way, any method you use, you should end up with the same solution. Power, again, is V multiplied by I. The energy, you need to integrate the power from 0 to infinity. And in this case, you should get something like this. And remember, this is the energy delivered to the resistor. This is not the energy generated by the capacitor. So the energy generated by the capacitor is 1/2 C multiplied by V squared. And as you can see here, as the time progresses, we have, first of all, the initial energy delivered to the capacitor, to the resistor, is going to be 0, because here, if you evaluate T equals to 0, you should get 1 minus 1, which is 0. Then over the time, you will see that the energy has been completely delivered to the capacitor. So any question, Shabab? Is it clear? Okay, Mohammed?
So, Doctor, if we want to solve a question, we start by finding tau and V initial, and then everything, we can do everything after that.
Exactly, and let me outline the steps of calculating the natural response of RC circuit. So the first thing, like you said, Mohammed, the first thing that we need to do is actually to find the initial voltage V0. Then we can find the time constant. Remember, this is the time constant after moving the switch or closing the switch or opening the switch. After that, we know exactly, we have everything we need to, all what we need now to do is to substitute. And in this case, it's going to be, for example, T greater than T0. So any other quantity you can find using this substitution. Any other quantity you can derive from the voltage. Does that answer your question?
Yes, thank you.
Okay. So it seems very straightforward, very systematic way. So let's have an exercise. So in this exercise, we have the following scenario. We have a circuit with a 100-volt source, and the switch was at position X for a very long time. Then at T equals to 0, the switch moves instantaneously to position B. So what we are asked to do is we are asked to find VC t for t greater than 0. So let's okay. Let me just solve this myself, and I will ask you to participate in the remaining parts. Okay, Shabab. So pay attention here. In order to solve such a problem, you have two time instants. You have something or two time periods. You have something before the switch is when the switch is position X. You have something when the switch is position Y. So in order to visualize things, so the first thing you need to do is you draw the circuit for each period. So when the switch at position X, we have 100 volt, we have 10 kilo ohm resistor here, and we have capacitor. But since it's a DC source and the switch at position X for a very long time, so the capacitor will behave like an open circuit. And this is VC of t. So just before the switch is moved to Y, we have V0 minus equals to V0 plus. Remember, the current passing through the capacitor or the voltage across the capacitor cannot change instantaneously. And this is going to be equal to, because there is no current passing through the 10 kilo ohm, it's going to be equal to the 100 volt. It's going to be equal to 100 volt. Okay, so this is what happens in the first period. The second period is the switch moved to position Y. In this case, the source has been disconnected from the circuit, and we have the remaining parts of the circuit. So let me draw it here. So when the switch so the value of this one is 0.5 microfarad. Remember here, I'm asked to find VC. So in order to find VC, I need to find back here, I need to find, and this is VC, I need to find V naught, which is I did find, and I need to find tau, which is the time constant. So remember, the time constant is R multiplied by C. I only have one capacitor, so C is 0.5 microfarad. But what about R? Which R? Should I use 32? Should I use 240? Should I use 60? Which one? What do you think, Shib?
Equivalent.
Okay, how to find that? Ibrahim, can you raise your hand, please? Okay. طيب, Ziad?
The resistance that are seen by the capacitor, which has
The thickness between the capacitors, which is in this case is going to be 80 kilo. Okay, so now I have everything I need. I have tau. I can easily substitute. So tau R multiplied by C and in this case is 40 milliseconds. I found the initial voltage. In this case, VC of t is going to be the initial voltage, which is 100, e to the power minus 25. Remember, 1 divided by 40 milli is 25. And the unit is volts. And this is valid from t for t greater than or equals to 0. Jaziz's question? Okay, good. Right. The second thing is asking us to, or the second part is asking us to find V naught. So what is V naught here? V naught is actually the voltage across the 240 and 60 kilo ohm. Can I find V naught based on the value of VC? What do you think, Shiva? Amar?
Maybe using the current divider, voltage divider.
Yes. So we use the voltage divider. So in this case, I have the equivalent resistance of 60 and 40, 240 is going to be 48. So let me just write it down here, 60. And 48 plus 32 is 80 multiplied by VC of t. And in this case, I'm going to end up with 60. The unit is volt. And remember, this is valid for t greater than or equals to 0 plus. Because at the moment when the switch is open, at the moment when the switch at position Y, the voltage across it is 0 actually. Okay, what about I naught here? Can I find I naught? Okay.
We can find it using Ohm's law.
So I naught here is going to be V naught divided by 60K. And in this case, it's going to be e to the power 25t milliampere. And this is again valid t greater than or equals to 0 plus. Okay. The last thing is been asked is the total energy dissipated in the 60 kilo ohm resistor. Okay, so what is the total energy dissipated in the 60 kilo ohm resistor? Shabab? Okay. Okay. Same people. Daziz Al-Hamidani.
Yes, Doctor. Can I see the 60?
This is the 60.
So it will be I naught multiplied by V.
I naught squared.
Yes, I naught squared. Yes.
Yes. So the energy will be the integration of the power. The power is I naught squared multiplied by R, in this case 60. So if you do the multiplication, you will end up with something like this. Yeah, doesn't matter in this case. So this is going to be 1.2 millijoule. So this is the energy dissipated by in the 60 kilo ohm resistor. Okay. Okay. We can have as many exercises as we want in this subject, but the good thing about it, they have some sort of systematic way of solving them. So probably solving one will be enough. Umar?
Yes, doctor. On the previous question, is it shouldn't be minus 50 t? The integration.
Yes, minus 50, this one. But the minus and 50, they are kind of like, okay, yes, this is minus 50. Okay. So let's see what we did. In the previous lecture, in this lecture, in the previous lecture, we talked about the inductor or the capacitor discharging after closing or opening the switch. You have a switch, and they are initially charged, then they discharge. And in this part, we're going to be more concerned about the capacitor or inductor. They are experiencing, or like all of a sudden you connect a source to them. So the capacitor or inductor are charging in this case. So the previous cases, there were cases where the capacitor and inductor are discharging, and in this case, it's the case when the capacitor or inductor are charging. So the previous case, they're called natural response. So discharging response is the natural response. And this case is called step response. Step response is all of a sudden you apply a source. And this comes from the fact is there's kind of like a well-known function, it's called step function. And it's something like this. So it's 0, then at t equals to 0, it's constant. So we can think about applying the source is exactly the same now. So if you are observing the circuit for t less than 0, you see the circuit doesn't have any source. Then at t equals to 0, you apply the source immediately or promptly. So the derivation here is exactly something or somehow similar. Probably we need to modify the differential equation. And as a matter of fact, the differential equation in this case is going to be a non-homogeneous differential equation. So the previous one is homogeneous, which means the value equal or the constant is 0, and in this case the constant is not 0. So let's try to derive what happens. So initially we have the following circuit. We have a resistor in series with an inductor and in series with a voltage source. So what we want to do, we want to study what happens when the switch is closed. So let's see what happens. So when the switch is closed, we have applying KVL. We have minus or Vs. At this stage, we know that we have minus and then we move. Ri plus L di by dt. So this is again a differential equation. So let me write it in a standard way. So in this case, I will divide. The standard way is to divide the coefficient. Make sure that the coefficient of the highest derivative term is 1. So in this case, it's going to be Vs divided by L equals to R divided by L multiplied by I plus di by dt. So let me move the derivative term into one side here. So I will have Vs divided by L minus R divided by L multiplied by R. Okay, so let me take R divided by L as a common factor, or minus R divided by L as a common factor. So in this case, I will have I minus Vs divided by R. Okay, I did not do anything. I just rearrange the equation and make sure that everything is kind of like in a standard way in this case. Okay, the reason for taking R divided by L as a common factor is we want the coefficient of I to be 1, and the reason for that is something like this. So if I divide both sides by I minus Vs divided by R, I will get I Vs divided by R multiplied by minus R L dt. So you can see in the left-hand side, we have all terms are a function of I. In the right-hand side, all terms are a function of t. So we can use the separation of variable method. So in order to find I here, we need to integrate both sides. So if we integrate both sides, starting from I naught, the initial current passing through the capacitor, IT d alpha minus Vs divided by R equals to, at this stage, probably we are familiar with the integral of, so let's assume that we integrating from t equals to 0 to t minus R L dx, for example. Okay, now if I solve the integral, here it's going to be the natural logarithm of sorry, I minus Vs I of t minus Vs divided by R divided by I naught minus Vs divided by R equals to minus RLT. So remember, my goal here is to find I. So I need to take the natural exponent of both sides. If I do that, I will get I of t, or E of both sides. I will get I of t equals to Vs divided by R plus I naught minus Vs divided by R multiplied by so note that this is exactly IT I final plus I initial minus I final. So let's see why this I initial, I final plus I initial minus I final. So at t equals to 0, the initial current passing through the initial current circulating this circuit must be equal to the initial current of the capacitor of the inductor, because the current passing through an inductor cannot change instantaneously. So what's the initial current here is I naught. So if we substitute t equals to 0 here, we can see that you will have I final plus I naught minus I final, and the exponent will be 0. And I final minus I final will be 0, and you will end up with I naught. Okay. The final value is when t equals to infinity. So in this case, when t equals to infinity, the switch been closed for a very long time, so the inductor will behave like a short circuit. So the final value of the current will be by Ohm's law, Vs divided by R, right? And if we substitute here, we'll see that if you substitute t equals to infinity, then the exponent term will be 0, and you will end up with I of t equals to I final. So this kind of gives us a standard way of solving for such a problem. Find the initial current, find the final current, find the time constant, and the solution will be in that form: I final plus I initial minus I final multiplied by e to the power negative t divided by the time constant. Okay, so what does the time constant represent here? In this case, the time constant represents, in this case, the time constant is representing 60 when the value of the current reaches 63% of its final value. So let me write it down here. Note that, again, this is the last thing I'm going to explain. Probably the only thing missing is finding VT. Note that 1 tau is when the current reaches 63% of its final value. Okay, so if I want to find VT, then in this case I need to simply differentiate. So I will end up with L R divided by L I naught VS R okay. So if we're going over time, I promise you this is the last thing. If I simplify it, I will end up with okay. This is the voltage. This is the expression for the voltage. Okay, so that's it for today. Just remember what we did. We started with the parallel RC circuit, the natural response of a parallel RC circuit. Then we moved to the step response. What happens if we have a source and all of a sudden we connect the source to a series to an RL circuit? And we show that we have a systematic way of solving this problem. Just we need to find the final value, the initial minus the final, and we need to find the initial value, the final value, and the time constant, and that should give us the correct value or the expression for the current. So yeah, next lecture inshallah we'll solve an exercise on this. Then we move to the natural response or the step response of RC circuit. Any question, Shabab?
يعطيك العافية دكتور.
Allah. Please do not forget to upload your quiz before the deadline. عمر.
دكتور هل حنا مطالبين نعرف كيف نسوي differential equation ولا بتكون جاهزة؟
No. The type of questions will be similar to this question, the one we solved so far. And you remember we did not have to solve the differential equation here. So we already know the form of the solution.
إيه تمام شكرا.
But it's very important to derive things. This gonna give you like intuition about how things are going to, or from where we derive these things. Okay, any other questions, Shabab? Okay, الله يعطيكم العافية إن شاء الله. توفيق.
الله يعافيك.